So after the what we did about this model, describing the model and building the model, we will be conduct some diagnostic tests. So the first question that we would like to answer is the overall model significant or no? Then we will be looking at if the overall model is significant, what variables are really significant for that model, which ones that we can really use for prediction purposes. Next question we will be answer is the standard deviation of the model error, the standard error, is it too large? If it's too large, it's not going to provide good results or meaningful results. The following question that we would be answering is, do we have any multicollinearity issues or no? The final question, which is going to be check the assumptions of the regression analysis. So let's focus on the first four diagnostic tests. So the first one, we're going to see whether the model is significant or no. So what we use the betas. We check the betas. The null hypothesis is going to be beta 1 is equal to beta 2 is equal to beta 3 is equal to beta 4, etc. to 0. And the alternative hypothesis is going to be at least one of the betas is not 0. So this is going to be our test. So for this problem, again, we still have the same problem, the one that is talking about the attendance, the game attendance. We are studying whether the significant or the model is significant or no. We are going to take the ANOVA. We are going to take the ANOVA. So what is the test we are going to conduct is, let me copy this here. We have 4 in this question. We have 4 betas, right? Beta 4. So are all these betas equals, or at least one of them is, are all of them equals and equals 0, or at least one of them is not 0? This is alpha, not A. To do this, we are going to look at the F value from the ANOVA. So this is the ANOVA. So this is the F value, or the corresponding P value. It seems that, look, the P value is 0, is less than alpha, so the model is significance. The overall model is significance. So significance in what? In explaining the variation of the response variable, because the P value is less than alpha, so we reject the null hypothesis. So at least we have one of the slopes is not 0. One of the slopes is not 0. So this is what we're going to say. One of the slope is not 0 and p-value is 0, so that's why the overall model is significant. The second idea is, if the overall model is significant, then what? Then what? Which variable is really significant? All of them are significant or no? To do this, actually, we're going to conduct this hypothesis, which is about, we're going to do the individual, like testing, individual for each beta. So beta I is 0, H naught beta I is 0, given that all of the variables are already in the model, or at least one of the betas is not 0, given that all of the other models or variables are already in the model. So we're going to check every single beta, if beta 1 0, beta 2 0, or beta 3 0, and beta 4 0, 0 or not 0. So to do this test, we are going to use either the F test or we are going to use the T test. We can use both of them. The t-test, we can use, again, t-test or f-test. The f-test can be taken from ANOVA. So the f-test can be taken from ANOVA table, while the t-test can be taken from the coefficient table. So both of them are correct. So the one that from ANOVA, we know that this is the one that's going to come from ANOVA. This is the guy. So I'm going to copy it and paste it already. So these are the values that we're looking for, all of them. So are these individual values or variables significant or no? So we can look at this one, or we can look at the coefficient. So both of the, where's the coefficient table? This is the coefficient table. We look at the t value and the p value. So again, we're looking for all of these guys, all of these variables. But the question is, which one's significant? It's clear that p values, we look at the p value, which one is 0? Is this guy, right? This one is the, yes, this one is the significant. And again, the p value is the same, it gives you the same result. So if you use f value or t value, both will give you the same result. We have only team winning losing percentage, the significance one. So that's why we are going to use this. I mean, this is the significant variable. Others are insignificant. For prediction purposes, we have to take off all of these insignificant variables and continue with the predictions. Just use the one that is significant. And it's worth mentioning that there's a relationship between the f value and the t value. If you look at the t value, if you square t value, you get f value for each. So what can we conclude? We can conclude only one variable is significant. We reject the null hypothesis, and this is going to be the winning losing percentage. So it is the significant variable. As I said, if you have insignificant variables and you would like to do some prediction, what you have to do is just take off all of these variables and build the model again. So we are answering actually the question, so I should have cut this and paste it somewhere here. Now, because we have 4 variables, we have to do this for all of the variables. So this has to be done for all of them, but because we have the tables, there's no need. It's for B1, then for beta 2, and beta 3, beta 3, and beta 4. We look at the tables, we found only one of them is significant, then we are done. The next thing we have to do is look at the standard error. So we need to look at the standard error, MSE, the square root of MSE, the square root of MSE. So the standard error, if you note that the standard error of the estimate is the square root of MSE. So actually, if you have MSE, take square root of MSE from ANOVA table, you get you get the SE, standard error. So the question says, estimate the standard deviation of the model error and discuss whether the regression model is acceptable as means of predicting the football attendance at State University at any given game. So we need to study whether the number of or the error is really acceptable. So what we have to do, we just look at where is the error. We look at the error from this is the error from the model summary, from the standard deviation of the model error can be found in the model summary. The S value, S equals 1184. Or you can find it in ANOVA. Where is ANOVA? This is ANOVA. It's the MS square root of the MSE. It is MS of the error. It's the square root of the MS of the error in ANOVA. This is in ANOVA. This is in ANOVA. So actually, it is the square root of 140, or what was the number? It's actually 1 million. Yeah, correct. 402,151. So this is technically the number. So if you take square root of this guy, you're going to get the S guy. So you should know both of them. So the idea is, if f squared is high, if you have if r squared is high, and the standard error is also high, so actually it's hard to get good prediction intervals or confidence intervals. So what is the rule that we are going to use to say that this is within the range or it's not within the range? We are using plus minus SE. So if the mean of the dependent variable is within plus or minus 2 times the standard error, then this should be practical. This should be fine. So to do this, let me write this down. We wrote this down. Then we should check the 2 times S. If we check the 2 times S, what we get? 2 times S is, we get positive negative 2,368. And we can look at the mean attendance. The mean of the attendance, where is the mean of that? It's not here. So let me go to basic statistics, descriptive statistics, game attendance. So this is the mean of the attendance. So the mean of the attendance is 15,897. So we're speaking about the range. So the range would be acceptable. So you're adding and subtracting 2,368. So the range could be, in this case, acceptable. The error, it's within 2,000 attendees, right? So we can say, yeah, it's fine. But the question, if the range is not acceptable, if this is not acceptable, what we have to do? Maybe we have to take some actions to reduce the standard error or the standard deviation of the estimate. To do this, maybe we are going to have more sample. Increasing sample, helpful actually. So we summarize this. It's fine, it's acceptable. And the last idea we're going to cover today is the multicollinearity issues. What is the multicollinearity issues? The multicollinearity, it's if we have a really high correlation between 2 independent variables. Because if you have high correlation between 2 independent variables, that means they are contributing and producing redundant information to the model. So when highly correlated independent variables are included in the model, they affect the results. They will affect the results. So some problems that we can tell, or like consequences or something, problems that the multicollinearity could cause. The results, actually, sometimes the signs, positive, negative, you're going to have something not clear. So you are going to see negative correlation. However, the correlation is positive, actually. The second thing that we might have is there is a change in the values of the previously estimated coefficients when a new variable is added to the model. If you add a new model, you're going to have a really different, kind of a sizable change, actually, in the estimated coefficients, because just we're adding one variable. The other thing that you're going to notice is sometimes a variable that was not significant or was significant then becomes insignificant if you're adding another independent variable. So sometimes you are switching between significance and insignificance because just you're adding one variable. This is some of the signs that we have a multicollinearity issues. And the estimate of the standard deviation of the model error increases when a variable is added to the model. So what to do? The idea is what to do. We are going to check something VIF value. If VIF value is greater than or equal to 5, then we say, hey, there is a multicollinearity issues. So VIF. And we check the signs of the correlations. Does the sign of the regression coefficient consistent with the sign on the correlation coefficient between the independent and dependent? We have to look at the sign. So we look at the correlation matrix and we look at the equation or the betas. If they are matching, then we are good. If they are different, that means we have something. We have issues here. Or if you have like you believe that there is a positive relationship between the two variables, then you found out in your calculations you found out no, actually you have negative correlation. Then you have to. There's kind of a trigger now. Hey, there's something wrong. So technically, we are checking the VIF. As I said, the VIF is the one that we're going to see from the model, from the tables, and look at this number, which is the variance inflation factor. It's a measure of how much the variance of an estimated regression coefficient increases if the independent variables are correlated. If VIF equals to 1 for a given independent variable, this indicates that the independent variable is not correlated with the remaining independent variables. The greater the multicollinearity, the larger the VIF. And VIF is calculated based on the R squared. Look, R squared 1 minus R squared J sub J, because we're taking 1 out. So to do this, we're going now to check in our model, do we have any multicollinearity issues? So the first thing to do is we're going to look at the correlation coefficient. Where's the correlation coefficient? The correlation coefficients, we did not find them here. Let's find them quickly. These are the coefficients. The game no, we will be, let me repeat this because I don't want to get, by the way, the dependent now. I'm going to take off the dependent. Just we're going to look at the independent variables. What are the coefficients among these guys? So look at them actually. They don't look that they have, it's scattered, everywhere scattered. Doesn't seem like a linear relationship or strong or something. And we can tell from the numbers. A team winning losing percentage, maybe we have some concerns about games played versus team winning because 0.5, we may have some positives, kind of moderate relationship. But the rest are kind of small numbers. So we don't have a really strong relationship. Again, to do this specifically, we have to look at what's so-called the VIF value. The VIF value is the one that tells you everything. Here we can say something, but it's not actually 100% accurate. And again, we're looking for the correlations among what? Among the independent variables only. So we have to copy the table and paste it here. Then actually we are going to go to the coefficients, and actually I think I added that one. Let me look. We do not have the coefficient. Where's the coefficient? Here's the coefficient. Yes. Look at the coefficient. The coefficients fable, we do have the VIF. VIF, look, for the independent variables. So all of them are less than 5, right? So we do not have any multicollinearity issues. So all of them, actually, the one that we care about is the one that what's so called is the one that team winning losing percentage, the one that actually it is in the model. So what can we say? We do not have any multicollinearity issues, and we report all of the VIF values. If there is one greater than 5, actually greater than 5, then we can say, yeah, we do have problems here. After that, we are going to build the confidence interval of estimating of the regression coefficients, as we did in the simple regression analysis. The confidence interval of the estimation of the regression coefficients, beta 1, beta 2, beta 3, beta 4, etc., all of them. So to build the confidence interval estimate, we are going to look at the coefficients table. This is the coefficient table. We don't have the estimate, so what we are going to do, we're going to repeat the test, regression. I'm going to go probably to results and have the expanded tables. Expanded tables, we are going to have this guy. It's expanded now. So I'm going to copy the coefficients. Develop 95% confidence interval estimate for each of the regression coefficients. So each of the regression coefficients, again, this is beta 1. Oops. This is beta 1, this is beta 2, this is beta 3, this is beta 4. And this is 95% confidence interval estimate for each of them. So to comment on them, let's say that we want to comment on the temperature. The temperature is negative 55.5, and the 95% confidence level is between these two numbers. So the first we start with, if we hold all of the other variables constant and use 95% confidence level, then the change in the temperature by 1 degree is estimated to generate an average change in game attendance between negative 192 to 81%. So it's going to be really big gap actually, right? Also, we can think about the team attendance percentages. The team attendance percentage is here, right? So if we hold all of the other variables constant and we are using 95% confidence level, then the change in team winning losing percentage by 1% is estimated to generate an average change in game attendance of between 30 people to 96 people or persons, right? So this is the way that we are interpreting these numbers. So this is everything about chapter 15, and yes, that's it. Then we can actually build any prediction model based on one variable. We ended up actually having one variable that is, making the difference, which is team winning, losing percentages. Thank you.